Hey everyone, welcome to the Allora Research Fireside Chats, where we explore the key ideas shaping decentralized machine intelligence and AI. So today we're unpacking the Cassandra problem. Why do consensus-driven systems miss rare but critical signals? And how can Allora's context-aware inference synthesis, how does that designed to surface and reward finding these signals? So I'm joined by Diederik, our chief scientist, whose team has recently published a new paper on this topic. Welcome, Diederik.
Hey, Steve.
So shall we start with the basics? What is the Cassandra problem in the context of AI?
Yeah, that's a great question. Actually, makes me go into Greek mythology. Cassandra was a priestess of the Greek god Apollo, and she basically made a deal with Apollo that she would gain the talent of foresight, so would be able to see the future. But the deal was that then she would engage in physical activity with Apollo, to put it that way, and she refused. So obviously Apollo got a bit mad about her breaking that deal and cursed her. And he cursed her such that her prophecies would be true, but nobody would believe them. And Cassandra was a priestess in the city of Troy. And during the Trojan War between the Greeks and the Trojans, she foresaw that the Greeks would put this giant wooden horse in front of the gates and hide their soldiers in there, that the Trojans would bring them in, and that the Greeks would sack the city. And she tried to alert the Trojans, but as the curse went, nobody believed her. So that was a key example of a human, in this case, being able to predict the future very, very well. And nobody believing her at that time. It didn't end up very well with her, by the way. She survived the sacking of the city, but died at the hands of the Greeks a little bit later. So that problem is not just a problem in an ancient myth, but it's actually a problem in AI. And it's a fairly well-known problem. In centralized AI settings, there have been solutions for that problem. In decentralized AI settings, it's not been solved yet until recently. And it's an even bigger problem in decentralized AI than in centralized AI. So that's why it's so relevant, and that's why I guess we're talking about it today. In AI, something very, very similar can happen, especially in the decentralized form. If you have many different models and you're trying to figure out which of those models is better, and in AI or machine learning, that's usually done through what they call ensemble methods. If you try and figure out which one is better, and therefore when you're trying to aggregate the predictions of these models and combine them into a single prediction, you would typically assign weights to these models. And most of these ensemble methods in AI and machine learning are basically using a form of historical reputation, so how well each model did historically. And if you have a model that has historically done well, but now you're dealing with this sort of unique situation where it doesn't do well, but there is this other model that does do well, then you would basically put your money on the wrong model. You would weigh the wrong model very heavily. And that is basically a form of context ignorance. You don't know, like, okay, which model should I trust when? And that is, in essence, is the manifestation of the Cassandra problem in AI.
Right. So just to kind of take it back to ancient Troy.
Yeah.
So the idea here is, I guess the analogy is that every day, so King Priam, he was in charge of the Trojans, and every day he would have to make a decision on where to put his resources, where to put his armies and things. And so I guess he'd have a whole bunch of generals that would be, would have different. So maybe General Chaos knew siege warfare, and General Anarchy would know naval tactics, whatever. And every morning they would come to Priam and make a prediction for what the Greeks were going to do, and he would have to take all so they'd be like the different models that we'd be predicting, and King Priam would have to make a prediction for or take all these ensembles from the general and then decide what to do based on that. Make an overall prediction weighing what the different generals were. And I guess because the king would have known the general's past performance, he could weigh up and make his decision based on that.
Yeah, indeed. And these types of mechanisms are basically like, in this case, it's like in the example you're giving, it's one monarch making that decision.
Yeah.
But, in a decentralized setting, it may be based on consensus or voting. But these types of systems are really designed for like average case accuracy, is like what would be good on average. And that completely breaks if you have non-stationary conditions. If you have changing conditions, then one model might be good at one moment, another model might be good at another moment, and then being right on average is just a way of kind of always being wrong, and that is what you want to get around, right? So it's basically the Cassandra problem is not. Imagine you have a model pool where every model is sort of an expert in a certain regime of the problem they're trying to solve.
Yeah.
Then the Cassandra problem is not about the fact that they're necessarily bad experts, but the problem is about assigning the good experts under the right conditions the right weight. So it's basically it's an aggregation problem. Is how do I combine all of these predictions in the way that is right when I have experts that are not always right, are actually infrequently right, but when they are right, they're very decisively right.
Yeah.
And then I would need to listen to them. So it's really a selection problem, and that's the problem that needs to be solved. Is the system needs to know a way of who to listen to right now.
Right. So it's a context. So the ensemble approach has no context awareness.
That's right.
Yeah.
No, not by default. No.
Yeah, exactly. So it could be, I guess, going back to the Troy situation, it could be the case that so there's lots of experience within Troy, and knowing whether sort of if it's going to be a naval attack, you should listen to General Anarchy and upweight his opinion on what to do and how to redistribute the troops or whatever. Yeah, that makes sense. So then maybe going forward, then how does this general approach, this ensemble approach, I guess the problem is that it will silence people like Cassandra, right?
Yeah.
So what's how does that happen? How is Cassandra silenced in the case, which ultimately leads to the fall of Troy?
Right. So I mean, originally, the sort of ensemble aggregation mechanisms were designed for, or basically were a way of acknowledging that model predictions are noisy. So on average, they might be roughly right, but they deviate from the correct prediction just through noise, or maybe like the ground truth, the target they're trying to predict is noisy. Like there are all kinds of noise involved in prediction algorithms or efforts. So if you know that the individual predictions are going to be noisy, then one sort of standard statistical way of getting around that is by just combining a lot of different independent models of which you know that the noise is not correlated. So one model might have a noise spike in one direction, and then the other model might have a noise spike in the other direction. You combine them, these two noise spikes cancel if you just average them, so to say. And that then results fundamentally in a better prediction.
Yeah.
But that completely disregards the idea that these noise spikes might actually be domain-specific expertise. So it might be that a model says, oh, wait, this is exactly the thing I know. And that's why I think the prediction is going to be like this. Whereas, in all other cases, it didn't know, had no idea. And then it doesn't work. Maybe a concrete example is if you look at financial markets. In a financial market, often what you see in price history is that there is an uptrend or a downtrend or a crabbing market where it sort of stays more or less constant. And there exist models that are more effective in specific domains. There are some models that are great at predicting crashes. There are some models that are great at predicting sort of more of the crabbing markets. And Now imagine if you have a price history where a lot of that price action has been crabbing. Then if you trust the average model, it's not going to get the crash right. And this is the thing: is the moment there is a regime change, this whole idea of aggregation to cancel out noise is a failure mode. So this historical reputation basically that crushes the context that you need, and it structurally suppresses specialists, experts. An expert is going to be right in one specific case, and what you need is a logical system that can recognize the context and then pick the right specialist for that context. And in the paper that we recently published, what we basically did is we proved that you can use machine learning models to empirically observe this, to observe this process, to basically teach a model to teach it when which other model is good, under which circumstances. That itself is a machine learning problem, because the context in this case is just a tenuous thing to grasp for a model, right? So you need to figure that out, and that is basically what we proved.
So before that, so you mentioned, I think, noise a lot in here. I'm trying to bring back noise to, I guess the Trojan problem where Cassandra finds herself. So this idea of noise is, I guess, how uncertain someone's predictions are, right? So if you've got the different generals, and you mentioned a noise spike, can you put the noise spike in the context of the Trojan? Of the generals making predictions?
Yeah, I mean, I think a famous analogy too is that when you've got a patient in a hospital, when you've got a patient on an operating table, it's not a good idea to put like 20 doctors around them.
Yeah.
Right? They will disagree on everything, and that's the noise, right? Yeah. So I can imagine the same thing with a bunch of generals arguing about what the best strategy is. And that's the noise, and then you sort of take the average, and in this case the king will have learned how to do that well. Yeah. But it completely disregards the fact that maybe one general is specialized in naval tactics, and the other one is specialized in like barricading walls. I don't care, but that domain expertise is in the end what is important. So it's basically about, in this prediction challenge, it's about predicting who will be right next.
Yeah. And is there so that's talking about their expertise, but there also might be things, for example, you can imagine that General Chaos has got bad allergies, so in summer his predictions are just terrible because his mind's all fuzzy, or General Anarchy fears the number 13, so on the 13th of every month his predictions are just like completely wrong. So and you can imagine that's obviously a silly example, but there will be, like, even without your Cassandras, even just on the generals, they will each have this sort of context, and if you miss that, your model will be worse, your predictions will be worse.
Yes, absolutely.
So okay, so I think you've alluded forward to how this can be fixed, but I think before we get there, so before solving the Cassandra problem, and we'll get to see how Allora does that, I think it's important to take a step back and understand what is inference synthesis, and why does that become a core bottleneck for a kind of swarm style intelligence?
So inference synthesis in general is the process of combining or coordinating multiple different inferences or predictions into one sort of aggregated prediction, one coordinated combined prediction. And as said, there are different ways of doing this. Like the simplest and most classical way is saying, okay, how well has everybody done on average over the past 10 years, and assign everybody a weight based on that. That's what we do not want to do, right? In this case, Absolutely. We want to have a form of context-aware inference synthesis. And you need to keep a couple of sort of boundary conditions or prerequisites in mind when you try to solve that problem. Everything like this is much simpler if you run everything on one machine and try to figure out how to combine different models on that one machine. But if you're dealing with basically a huge decentralized model pool that you need to combine, then you need to be a little bit more more subtle about it. So you need to sort of coordinate a group of models with the same goal, the same target. And within Allora, we do that within what we call topics. So a topic is kind of like, is a subset of network participants that try and solve a problem according to the same rule set. In many ways, it's like a sub-network. So they have a specific target, specific loss function or objective function they're trying to optimize for, and a certain rule set that governs their coordination. And within, like, on each sort of inference cycle, which we call an epoch, the workers or the models within such a network will submit their predictions. And if you just combine them based on historical reputation, you can do that, but you lose all of your context awareness.
Absolutely.
So the critical step is that we do within the Allora network is we've introduced a second type of worker, which we don't call the inference worker. The inference worker is sort of producing these raw predictions. Now, this one we call the forecasting worker. We call it the forecasting worker because they forecast the performance of the inference workers under the current conditions. So we're trying to solve a problem that is, a certain amount of time into the future, and they've done well in the past, or they've not done well in the past. And at any moment in the past, there existed a certain set of conditions, of circumstances. And then we look at what the forecaster model does is looks at the current circumstances and says, okay, given these current circumstances, if I compare them to all of the historical ones, can I find basically a relation between how well each inference worker did and the conditions or the circumstances at the time? And then I use what I learned there, look at the current circumstances, and predict for each inference worker how well it is going to do. And this is especially important when you have a swarm of models that is privacy preserving, like Allora does.
Absolutely.
Because in Allora, the models don't share anything really other than their inference. So they don't share their models, they don't share their data. So you have no way of knowing which one is going to do well under which circumstances other than actually learning it. So that itself is a machine learning problem. And that is the way in which we've been trying to solve it. So inferers predict the target, forecasters predict who will be accurate now, and then the network uses that information to basically weigh all of the original inferences, and for each forecasting worker does construct like a combined inference that way.
Yeah, nice. So trying to take this back to Troy again. So you're in this I guess Troy analogy. So the generals are like your inferers that are coming up with a prediction. And so the forecasting rule might be something like if King Priam had got a whole bunch of smart advisors, and their only job was to track what the generals had predicted each day. And over the 10 years, I mean, it's a pretty long siege, is to track over those 10 years and taking like the general conditions and every day see what the generals, when they were right and when they were wrong, but record all additional information that might help them predict in the future which generals would be better or worse in different. So, general anarchy is useless on the 13th of the month, or perhaps there's a farmer whose farm's in the West Field that is able to tell them when the train is impassable, so the Greeks won't be able to pass there. So I guess the forecasters are, rather than trying to make a prediction themselves, they're trying to understand the past predictions and the context for when the different generals have done well. Is that?
Yes. Yeah, that's right. And I think it is actually it's the critical ingredient, right? Because the king can't look in the heads of the generals either, right? So there too, there exists data and model privacy.
Absolutely.
So and in such a privacy preserving swarm, so to say, it's the synthesis, it's the combination of these signals where the actual intelligence is made.
Yeah, and the point is,
sorry.
Yeah, on you go.
The naive way of doing that, of just sort of historical weighting, that turns the whole system in like an expensive consensus machine.
Yeah,
and that doesn't work.
Yeah, and so the point of these forecasters, they're predictive, not reactive, right?
Yes.
And that's what would, so if these advisors or the forecasters had also been aware of Cassandra and her predictions, would have and her affinity for wooden horses would have, been shouting to the general, you got it 10 times the weight on Cassandra's because there's a wooden horse and she's been talking about wooden horses. So yeah, I guess that's good. So that's I think conceptually, it's smart and it's easy to understand that. But how does that work in practice? Like in terms of, so how does the forecasting task actually address the Cassandra problem in a more detailed way?
So indeed, what the forecasting worker does in this case is de facto a second task next to the original one of the inference worker that just says like, what's the temperature in London going to be tomorrow? That might be the goal of the inference worker. Yeah. And then the forecasting worker needs to figure out what the performance is going to be of each worker. So in machine learning, that's normally called the loss, right? So you can evaluate the proximity of an inference to the ground truth, the true value that usually is revealed later, otherwise it wouldn't be predictive. And that comparison you do through some function, you call it the loss function, and you get out a number, and that is the loss, and it signals how well that worker has done or that model has done. So the forecasting workers basically they forecast that loss under the current conditions, and then what the network does is it takes these losses and it converts them to weights. It uses a sort of mapping function for that, where in goes loss and out goes a weight, and it does that in multiple steps. So it does that for every worker. So for the inference workers, it basically says, okay, you've historically been this good, so this is what your weight should be. But then it also takes, for each forecasting worker, it takes all of its loss forecasts, and it says, okay, these are the losses. I'm going to make, for each forecaster, I'm going to make a separate sort of weighted, synthesized prediction. We call it the forecast implied inference. So you get all of those losses. Like model A is it's February. Model A is typically pretty poor at predicting the weather in London in February. It's usually really good in March, but February is awful. And then it turns out there was a west wind. Model B is really good when there was a west wind. So I'm forecasting that model B is going to have a better loss than model A. So that goes into this mapping function, means model B gets more weight. And then we combine these inferences, and that is the forecast implied inference for that forecasting worker. We add that to the total pool of inferences, and then the network learns, not just for the inference workers, but also for the forecasting workers, who's historically typically been right. So it learns which forecasting model is really good at this context-aware game of forecasting all of the inferer's losses. And this is why then in practice, the forecasters in sort of the overarching network inference typically get a very high weight, because they have this context-aware information that allows them to say, okay, this is all of the raw inferences that come in. I know that one is going to be good, that one is not going to be good. Based on that, we combine everything, and it turns out that's going to be a really strong inference. So the network learns that's a really strong inference. I should always put a lot of weight on that forecaster. And that is then combined. And what that means is that the network listens to the models that are predicted to be the best in this regime right here. London in February, west wind, and goes with it. And that is basically what then allows you to generate this sort of self-improvement loop, where the network uses the forecaster to be sensitive to these contextual signals and then learn which forecasters do that well over time. And of course, it could be that some forecasters get better, others get worse. So that learning has to be adaptive as well. It needs to use some sort of moving average, and that way the network can then outperform the pool. So to summarize, maybe what Allora does is it basically adds this sort of market-like layer of models that predict who will be right next, and then weighs them accordingly.
Yeah, nice. Okay, so that would be going back to the, I guess, the Greek, just to try and encapsulate that back in our, and these poor old Trojans have been there for 10 years, and so you've, the analogy might be that one general says the army's going to attack from the north, the other one says from the south, and these wise group of people would say, well, because it's I don't know, it's particularly cold, that this general is better at predicting, so it's better that they attack from the you assume they attack from the north, for example.
Yeah.
So how, and in a sort of concrete way, then how do you measure what the forecaster, how good it is, and how do you measure how much better it makes a prediction compared to not having that forecaster? What's the mechanism for that, for going into the weights? How does that work?
Yeah, so as mentioned, this actually is a really good question, because if you look at what I just said before, is I said that you can get this self-reinforcing feedback loop, right?
Yep.
Where you get better forecasts. So the forecasts are context aware and are picking up, okay, I should listen to this guy now and to the other guy later. That gives you better weights, which gives you a better network inference. And then because the network inference, or the combined inference, is less noisy, you get better feedback, better signals of what might be working well in the future. And the forecasting workers will use that in the future to create even better forecasts. So if you do this well, and if you are able to really isolate the right quantity that the forecasters should predict, and how to convert that into weights, then you can really make that feedback loop spin. You can make the whole system proportionally more effective. And that requires you to do two things. One is you need to define a context that the forecasters can pick up on. Yeah. And in traditional machine learning, this is called feature variables. It's basically the forecaster needs to learn what are the signals that tell me that general anarchy is going to be the guy to listen to, and general chaos is the guy I shouldn't be listening to, right? What are these signals? That needs to be identified. So that's one. And then, so it's not like some sort of like opaque, mysterious context. No, it's very quantifiable things, right? We've been giving some examples, like if it's cold and the fields in the north are wet or frozen, or maybe there's a west wind and it's hard to predict the temperature in London, or easier. Yeah. So these are very concrete things. But then the other thing that you need to choose very carefully then is how to capture performance, because that is then what they call in machine learning the target variables, the thing you're trying to predict. And if you predict the right variable, then it can be more meaningfully translated into a weight. Now, and that is something that's worth thinking about a little bit more. Yeah. So when you combine inferences, you're basically calculating a weighted average. What does that weight do, right? Should that weight reflect sort of the absolute performance of a model? Should that weight reflect how good that model is relative to maybe the network inference? That might tell you something like, okay, is this model positively or negatively contributing to the network? Or should your target say something about how good the model is relative to the other models? Now, these are all, in principle, are different goals, different ideas of how you would want to represent this. And you can mathematically express these in the right way. So in this specific example, like the absolute performance you could quantify that by just making the forecasters predict the loss.
Yeah.
Because the loss is the absolute performance, is really the proximity of, or the separation, I should say, between the prediction and the ground truth. Now, how far are we? And then you have the transformation, but it's the absolute performance. The second thing that I mentioned is how good is the inference relative to the network inference. So does it improve the network or does it worsen the network? And that is something that you would normally measure through what we call a regret. A regret is literally the loss difference, or the log loss difference. You can do this after taking a log of the loss as well, between the network predictions and the individual inferers, or the individual models' predictions. So basically, how much better or worse is the model relative to the network? So that's what we call a regret. It's basically, in this case, how much would, you can imagine it this way, how much would the network regret not having used that model instead of its own network inference? Yeah. And then the third option, where I said, okay, maybe you're interested in sort of the relative ranking between all of these models. What you would do is you would construct what we call a regret Z-score. And this is basically a simple statistical transformation, but what you would do is you would calculate the regret for every model. So for every model, you have a number that says, am I better on or worse than the network, and then by how much? You can also just do it for the loss, by the way, it doesn't matter. And then what you do is you divide those numbers by the typical spread, the typical standard deviation, the dispersion of these predictions. So it basically says, okay, the average model is then going to have, like, it's not better than the network, it's not worse. It's going to have a Z-score of 0, one that is unusually better than all the others will have a Z-score of maybe 1 or 2. That means it is much better than all the other models. And it's a way of ranking these models implicitly, right? The worst ones will have negative Z-scores. And that way you basically, you signal to the network, to the inference synthesis process, oh, well, this is going to be, irrespectively of whether it's a good prediction or a bad prediction, I don't care. It's better than all the other predictions. Yeah. So you should still weigh it strongly, right? And this is basically is a decision that you need to make. Now, that is the decision you need to make there. And what we showed in the paper that we just published a few months ago is that it is these sort of relative targets. So not the absolute loss, but the regret or the Z-score. These are the most effective at getting context-aware performant inferences. And that makes sense, because if you think about it, what does it mean to weigh model predictions? It means that you're out of the pool that is available, not out of some sort of mythical pool of perfect predictors somewhere. No, it's what you have available. You want to assign the high weight to the model that's better than the others. You want to assign the high weight to the model that is positively contributing to your network inference. And that is why these targets, so the regret or the Z-score, are the most effective, because they are basically the most directly tracing what the weight should be. And that is actually what we've now sort of experimentally demonstrated, is that works. And that then allows you to go back to your context, so to your set of feature variables, and very directly, provided you have a performant forecasting worker or a set of performant forecasting workers, but very directly map that context to the best possible weight distribution. So basically what that does is it makes every forecasting worker, it makes it responsible for whatever context it is sensitive to, right? There could be that different forecasting workers are sensitive to different contexts as well. And they're themselves responsible for capturing that context, but then at least by agreeing on what the target should be, and how you then convert that into weights, the network can best synthesize that. And what that means in practice is you don't need to be able to like perfectly predict the performance to solve the Cassandra problem. You don't need to perfectly predict what the loss is going to be. You could be off. Like all the losses could be like predicted by just some offset. Like I over predict all the losses, or I under predict all the losses. It doesn't matter. What is important is that you correctly rank the models in this context aware and context conditioned way, and then you solve the Cassandra problem.
Yeah, nice. So that's really clear. So back in the taking us back to Troy, after each day of the siege, so someone's writing down what the generals predicted versus what happened. And so in terms of a loss, let's say General Chaos said the Greeks would attack from the south, but they came from the north. So that would be a big loss. He got that completely wrong in a simple analogy. So that would be his loss. But then the point is you can combine the losses from all the different generals, and you can ask the question of how much better would the prediction have been without General Chaos. And in this instance, it would have been much better. He was the only one that got it wrong, let's say. So that's an idea of a regret. How much do we regret leaving out his inference? And so that, and then you can imagine you take that concept and you give all of the generals a regret, and then you can basically compare them and have a look at the distribution of these regrets, and you can combine that distribution in a smart way. So that's very clever. So I guess I'd like to dive into details if you don't mind. Mechanistically, how do these forecasts get turned into an influence? So how does Allora go from taking these forecasted losses to weights and then to a forecast implied inference? So really diving into the details here.
Yeah, sure. I mean, there is, by the way, I should also say, there is a huge amount of literature on like techniques that you can use for this. You know, there are many famous papers, and I think when we post this, we will include some of the papers that people can read up on if they're interested. But for Allora, or the solution that we're using here, we used techniques that are, I think, best suited for this problem that we're trying to solve. So indeed, what I mentioned is we forecast this, either the loss or the regret or the Z-score. So either the absolute performance, the performance relative to the network, or the performance relative to the other inferers. And then you can, if you predict the absolute loss, then you can very easily convert that to a regret, right? To the performance relative to the network. And then you can easily convert it also to a Z-score. So each of those targets can be converted between, but for a model, it's just better to predict the relative versions of that. So whatever you predict, in the end, it needs to be converted to some sort of regret. And what we do is we take these regrets, and then I mentioned this mapping function that we use, a regret to weight mapping function. And we use what is technically called a logistic gate. It's basically it's a sigmoid related function that assigns high weight on one side and very, very low weight on the other side, and there is some transition between both. So that is how we do that conversion. And then the weights that we get out, we use that to calculate a weighted average. In a little bit more detail, before we put these regrets into the weighing function, it is important to realize that these may change as a function of time. So sometimes maybe there may be a huge spread in regrets. Sometimes it may be a very small spread. So it's very hard to calibrate basically what the interval should be and how you then should map that interval to weights. And there again, we take this approach that you should be looking at the relative distribution. So we divide all of those numbers by the typical spread. And that way you can standardize your distribution of regrets before you pass it through that mapping function. So you say, okay, today the regrets range from -10 to 10. But yesterday they ranged from minus 100 to 100.
Right.
You can imagine that if you say, oh, we should give everybody a weight of 1 once the regret gets above 10, then you get very different results for these two distributions. So you need to standardize them. So we standardize them, and then indeed we pass them through this logistic gate. And that creates what I mentioned is like on the extremes, you get high weight or low weight, and there's some smooth transition in between. So that means also that when the inference synthesis mechanism or the network is unsure, it'll assign a little bit of weight, but not too much and not too little. And that also happens not just in sort of the overarching synthesis step, it also happens with the forecasted losses or regrets. So when a forecasting worker says, under these circumstances, I expect these regrets, then the network says, okay, well, for these, you're really certain because these are really extreme regrets. But for those you're not quite sure, we give some intermediate weight when calculating your forecast implied inference. Now, then when combining all of these inferences in like sort of the top overarching step, we do something additional. So for the forecaster, it's very important that you always use the instantaneous performance prediction. Like what is the performance going to be right now? But if you also do that during the overarching step, you're going to get a very noisy combined inference, because the situation may change, right? Somebody might do well right now and might have done well in the previous step, but that might be an exception. And maybe they did very poorly during the past, 1,000 steps, and it's only last two that they did well. Do I then systematically want to assign more weight to them? Well, no, of course not.
Yeah.
So you want to use some historical window over which you basically average their performance when you put together all of these models. And you don't lose context awareness when you do that, because we have the forecast implied inferences in there that use instantaneous expected performance. So the forecast implied inference is the context aware part. If the network learns that over long time scales, that is typically the right one to listen to, it will systematically assign high weight to that. And we use that using an exponential moving average to basically average over these long time windows. But that way you are adaptive, because that's what your forecasting workers do. They adapt to whatever is happening right now. And the network then learns over long time scales and adds the stability for that reason to listen to these sort of context aware and constantly adjusting models systematically. And then that stability is then what you need. So that is the sort of in the end, the inference synthesis mechanism. So it basically, through the forecasters, it's fast to adapt, but the overarching mechanism is slow enough to like not be chasing noise all the time. It is grounded in this idea of, okay, this is an approach that works well, and that's why we do it. It's basically systematizing how to be adaptive, and that works. And the combination with this sort of soft weight allocation, where if you're not quite sure, you assign a little bit of weight. If you're very sure, you assign a lot. If you're very sure that it's going to be awful, you assign nothing at all. That basically together makes the system very, very stable.
Nice. So you have a way of combining, because so just to sort of conceptualize that, the difficulty here is that on some days all the generals will make very similar predictions. On other days they'll make completely different predictions, and you need to have some way of systematically and uniformly applying that and be able to do it for both those situations. So the idea of this regret tells you how much better we think or worse each general will be, and then you can normalize it so the spread, even like it can treat both when all the predictions are very similar versus when they're very spread out in the same way. And this idea of this exponential moving average or the weighting takes account of the fact that each inferer will have its ups and downs over as time goes on. And what you really want is not to just be jumping every time. They've done well yesterday, so you have to look and understand that in the context of how their predictions have evolved over time. And this, so by doing this, it's, I guess, a systematic way of applying that to any problem. Really, the same things will come across any problem where you're trying to do this.
That's right. It's basically making sure that the system doesn't overreact all the time, right?
Yeah.
Yeah.
So can you maybe provide some examples where this like context dependent outperformance that we've been discussing, excuse me. So where is that crucial in AI applications?
So yeah, in many actually. If problems were if problems wouldn't need this, then you probably wouldn't need AI either. That is because if you wouldn't need this type of sort of context aware performance forecasting, then it also means the problem is stationary, stable, and it's probably not so it is boring, right? It's not so complex that you actually need AI to solve it. I think that is what happens most. So there are a couple of obvious examples of where this might shine the most, so to say. One is when there are basically periodic, or may not be periodic, doesn't matter. But if there are regime changes in the problem, and you have regime-specific specialists. So I gave this example earlier about a financial market that can be in an uptrend, a downtrend, or crabbing, or crypto markets are notorious for making impulsive moves. And then you want to, obviously in those different regimes, you have different prerequisites for the types of models that might be more attuned to these circumstances.
Yeah.
So, some models might be constructed to be performant only in specific regimes. And any form of naive averaging or reputation weighting would basically miss these types of performance windows. So this is time-based. What I'm saying now, right, is there might be a certain duration we're in an uptrend, certain duration we're in a downtrend, but it doesn't need to be time-related per se. Like the fundamental thing I just said there was uptrend or downtrend. It wasn't, it's February or March.
Yeah.
So the signal there is another variable than time. So that's important. So I said, indeed, you have specialists that are focused on a specific regime. Then the other thing I mentioned is that the problem is not stationary. So the problem changes. There too, you often need to be adaptive. You need to adjust as a function of time, because what it means is that the regimes that I was talking about just before change. And it means that a different specialist or expert is going to be better at a different moment. And that can be due to, shifts, due to seasonality, that's more fixed time, or structure breaks, doesn't matter. Shocks, like impulsive moves, as I mentioned. This is very real in real world applications of all kinds of AI. Then indeed the point is that the lowest average error tells you nothing. So you need to be attuned to these shifts. So then the other case where context-aware inference is delivering a real difference is in sort of tail risk or rare events.
Yeah.
The whole point about, I guess, the Trojan War and Cassandra's myth is that there wasn't a wooden horse in front of the gates every day for those 10 years.
Yeah.
Like there were 3,500 days without a wooden horse in front of the gates, and suddenly there was a wooden horse. I mean, that is tail risk, right? That is a rare event.
Yeah.
And in these, and it was high stakes as well, because being right at that moment would have changed history. Rare events with high involved risk are the other key moment where you want to be able to dynamically figure out who does that right. And it's a little bit tricky, right? Because it means that the forecaster should identify which circumstances signal that there is going to be that there is a rare event. But that is, in principle, is a less challenging problem to solve than actually predicting the target of the inference task correctly. So to give you an example, it might be that if we look at the banking crisis in 2007, 2008, it might be possible to recognize that there is a system shock coming in like the circumstances and conditions.
Yeah.
But it's a lot harder to tell by exactly how much the S&P 500 is going to crash.
Yeah.
Right. So that is why it's a good idea to separate these two roles. And okay, then what you do basically by having this sort of this context-aware risk signaling is you can introduce a form of reliability and trust that wouldn't really exist anywhere else, right? You by having the context awareness to say like, hey, something rare might happen, a system can adjust much more reliably than if that signal were absent and you just keep listening to general chaos who just loves wooden horses, wants to cuddle them. So yeah, that is the key insight here. Is a specialist often looks worse on average, and this applies everywhere. It applies in human society as well. Is a specialist is probably not going to give you the grand vision for the future, but they will be able to solve very specific problems in a way much better than maybe a generalist could, right? And that is why you need to have that sort of pool of specialists that you can play with. And in things like shifting markets or rare threats, that is where knowing the specialist is important. So the most important moments are the jumps or the discontinuities, and the system must learn who to trust at these moments of change.
So it's having this pool of specialists. But I guess so. I'm putting myself in Cassandra's position here, right? So Cassandra's banging on, and she probably had other predictions, and no one's listening to her. Like, why should she bother keep making these predictions? So what role do incentive structures play in ensuring that these underrepresented, on the long-term average, they're underrepresented, but really high value contribution? So basically, I'm thinking of you've got your generals, you've got your pool of Cassandras, and King Priam's super busy, right? He had 50 kids, so he was a busy guy. How does he, how do we make sure that we keep Cassandra interested to keep making those predictions? And also because it's such a high value, you mentioned the high value, like how do you make sure that Cassandra is appropriately rewarded? And also how do you maximize utilizing that information in the decentralized AI systems we've been talking about?
Yeah, I mean, you're touching on it, right? It's related to incentive alignment. You need to make sure that the forecaster in question, because that's what this is really about, the context-aware oracle, which in the context of this conversation is a forecasting model, forecasting worker, is incentivized to continue participating, even though it might not be rare always, or it might not be right always. Yeah. Now, in the case of Cassandra, I'm pretty sure she wasn't paid well to keep banging on about her predictions.
Well, she was Priam's daughter, so she was loaded.
Yeah, right. but also, I mean, it was quite obviously related to social pressure in that case. Yeah. Social pressure doesn't work very well on AI models, although in the current agent wave, I'm kind of seeing signs of like social networks for AI agents lately that I find very interesting. But in the more general case, of course, the incentive is not going to be social pressure here. What is important is that you create an incentive structure that pays not for popularity, but for marginal value. So in other words, how much better or worse is the network with this forecasting worker present relative to without? And this is something that we do in Allora, not just for the forecasting workers, but basically for all workers. Instead of saying, okay, we're going to pay you based on like how right you are in an absolute sense, we realized very quickly that that is actually is not the incentive mechanism that works, because how do you convert that, right? What matters is how much better or worse, but let's assume better, is the network because of your presence. And that is what you need to reward in the end. So the way we do this for inference tasks and in part also for forecasting tasks is we basically we calculate what the network inference is in like through the normal process that we've been talking about. But then for each worker, for each model, we also calculate what the network inference would have been if we remove that one inference. And then we compare the performance of these two network inferences, which is like the normal network inference and the network inference without the contribution of that one model. Let's call it the one out network inference, where we removed one. And if the network is better when you include that model, and thus is worse if you remove that model, then that model, or that worker within the network should be rewarded more than if the network would not change much or would be worse. So with that model present, so would be better without that model. So that is how we're using one out scores in that context. But there is something important to realize here. So this might work for like normal inference workers, for just models that are trying to predict the temperature in London tomorrow. However, a forecasting worker fulfills a very important and unique task, because it basically enables this context-aware coordination between all of the inference workers. And therefore, it is in the interest of the network to have a degree of redundancy between forecasting workers. Now, that is not something that this one-out way of scoring does. Because now imagine I have multiple models that are copies of one another, predict exactly the same thing. Then if I remove one of them, then the network inference is not going to change much, because I've got many copies of it. So the network inference is just going to stay the same. And therefore, that model will actually get a very low reward. So that's an intrinsic part of using these one-out scores. It's extremely Sybil proof. It's if you have a performant model and you spin up many copies of it, you're actually just harming your own rewards by doing that, right? So copying is not lucrative. For forecasters, you kind of want copying to be lucrative, because if there is no forecaster at all, there is no context awareness. So it is really important to also look at, okay, now imagine a network without any forecasters at all, and imagine you would be the only forecasting worker. So we can also calculate these network inferences corresponding to these cases, where one network inference where we ignore all of the forecasting workers. We call that the naive network inference. And then for each forecasting worker, we just add that individually, like one at a time. And that then becomes like the one in network inference. And you can compare these and say, how much value does this forecasting worker add? And then reward that as well. And then that is what we do for forecasting workers. We don't just reward them based on one out performance, where we remove them, because there is a little bit of redundancy in the forecasting task. Like if two forecasting workers are both context aware in the same way, then, obviously they're going to provide very similar inferences. I don't want to slash their rewards because of that, because it's very important that they're there and they were right in that way. And it's a very important role. And therefore, we also added this sort of one-in way of scoring. And this is, I think, from a sort of bigger picture perspective, again, there's great literature on this. that we'll link below later. But the responsibility of designing the right scoring rules for any form of coordination layer is huge. You need scoring rules that incentivize exactly the right behavior, that keeps Cassandra around.
Yeah.
And because the rest of the network has learned to listen to Cassandra, now we need to make sure she's there, right? And therefore this sort of promotion of the forecasting worker in that sense exists. Also, I should say that if we look at the one out scoring of individual inference workers earlier, that is not just that doesn't just accommodate or account for the individual contribution of that inference worker, but also the secondary contribution of that inference worker through the forecasting workers. Because I remove that inference worker, and then the way we do this, we actually also we update all of the forecast implied inferences. So if I remove Cassandra, then also all of the forecasters lose their ability to include that inference. And when I then say, okay, how much better or worse was the network, it actually it has removed Cassandra completely from the entire calculation. So it's not just that Cassandra gets paid for sort of her direct contribution, she also gets paid for the contribution that the forecasting workers think she will make right now. And that is how we keep the Cassandras engaged, basically, is we pay people for the lift they add, and we don't punish redundancy in the context awareness because it's so important. And in the end, what that does is it incentivizes truth telling, right? Which is what Cassandra did. Yeah. Is you create the incentive structure that no matter what the truth is, whoever tells it will be rewarded for it. And in Allora, we've not really touched on this yet, but it is related to the reputer role, which is the third role next to inference workers and forecasting workers. Is the reputers have the task to basically evaluate what the performance or the loss is of every worker, of the network itself, of every worker, of every forecasting worker. And that way ground all of these mechanisms that we've been talking about in the ground truth. And that way, in the end, is the truth telling that actually wins.
Yeah, nice. So I guess this is trying to boil this down to it's a single concept. It's rewarding the unique contribution. It doesn't matter, for the inferers, so the generals, for the forecasters, so this group of experts who are helping provide the context and say, listen to these people. So on normal days, Cassandra wouldn't get very much, but on the day of the horse, when every other general is wrong and only Cassandra gets it right, then in the context of one out, if you take out her prediction, everyone else is horrifically wrong, but you add her in and she's absolutely bang on and gets rewarded. But likewise, the forecasters, so this team of people helping the king and provide the context, for all the ones that said, look, today there's a horse, you've got to listen to Cassandra, they will, for their contribution, will be very well rewarded compared to those that said don't listen to Cassandra or weighted her down a lot. And it makes sense that the more forecasters who it makes sense for them, if a lot of them are saying listen to Cassandra, they should each be rewarded, because that adds that adds power to the overall performance. So that I guess then that will keep Cassandra. So Cassandra knows her big payday is coming. At some point there's going to be a regime change. She knows there's a horse coming. So
that's right. She already knows. She knows when she's getting paid.
Yeah, she knows she's getting paid. Cool. So you mentioned this. You mentioned the Sybil idea. So a Sybil is where you spin up a whole bunch of different let's say workers, like 100 general chaoses all making prediction. They're all trying to game the system. So you explained how Allora is set up that just creating 100 copies of general chaos isn't going to make general chaos any richer.
No.
But focusing specifically on Cassandra, how do you keep like this Cassandra surfacing, find the Cassandra, how do you keep that robust, particularly against things like gaming, collusion, Sybils, and And I guess what we really care about is the truth. The risk of optimizing the metric instead of the truth. How does that work?
Yeah, and that is indeed where reputers come in. So reputers are basically their single task is to take all of the inferences, compare them to the ground truth when it's revealed. It typically takes some time, but then the ground truth is revealed. Reputers evaluate the loss function of the topic within which all of these participants are being coordinated. And that loss function is then reported back to the network. And the network uses that loss then to calculate its regrets. And that regret is then the long-term sort of historical reputation according to which the forecasters get weighted, the inferers get weighted in the overarching mechanism. So the reputers, in order to function, actually stake. So they put their money where their mouth is.
Right.
And by staking, they are basically defining the scope of their influence within the network. It also means the reputers themselves are rewarded not only in proportion to their stake, but in part, yes. In the other part, they are rewarded in proportion to their proximity to consensus with the other reputers. So if the reputers say, okay, well, the loss of Cassandra is going to be this and this number, then another reputer might give a different number. And then basically there is a consensus problem that is being solved. And that consensus problem is basically using an adjusted form of the stake. So it's an adjusted stake weighted consensus solution. So what that means is you need to put in capital, but you can't. It's why we use adjusted stake, not the raw stake. You also can't just pour in millions and for that reason just be right always. There is a form of deliberate fragmentation that's actually imposed on the reputer pool. So there was a consensus game there. They put in stake to provide the economic security for grounding all of the processes we talked about in the ground truth. And then because there was a pool of workers, of forecasters, of reputers, where on the reputer side, we use this consensus game, you build in a form of redundancy and system stability that basically keeps the system going long term. And that is what provides that security. So I described already how individual workers get scored, that basically rules out their ability to earn more rewards through copies. But here too, we basically introduce the role of reputers as a way that is also very, very clearly attack resistant. So this again is basically provides the key ingredients of what you need for a functional market. So if you think about just market design in general, what you need is truthful evaluation, and that's what the reputers are responsible for, and expensive manipulation. So the reason manipulation is expensive here is that every epoch, every prediction cycle is an economic opportunity, and both the reputers and the workers, be it inference workers or forecasting workers, are marginalized economically quickly when they don't do their jobs well. So it basically there is that makes manipulation expensive, and basically therefore the ability to remain relevant within the network based on this historical reputation requires performance, right? The reputation is basically the weight or the influence of the participants within the network, and updating that is a form of risk taking because reputers put their capital there, and if you then want to manipulate the outcome, that becomes a losing strategy because the reputer gets marginalized. We have a special defense mechanism there that's based on what we call listening coefficients. If a reputer is systematically disagreeing with the others, it will get silenced forever, basically. Well, not forever, but long term. And it's kind of like the X algorithm in a way. If people who are spamming are just getting silenced, and the same applies to reputers here. So it's basically what you have is the reputation and influence updates that the reputers carry out require taking risk, and therefore it is a requirement to do that well. So you want, in the end, you want a system, and then that's what we've designed here. And if you just zoom out and look at the context-aware forecasting task that we've been talking about, you want a system that rewards useful disagreement. Right? Useful, because then it contributes positively to the network inference, but only when it's grounded in reality and not when it's just adversarial tricks or noise or anything. So that is, in the end, what it comes down to.
Fantastic. So I mean that's a great description, and I can see lots of potential use cases for this, having solved Cassandra, not least the fact that Troy would still exist and history would have been different. But no, I mean, maybe just to, I guess, what the thing I really want to know is what's the broader implications of this? So Allora's solving the Cassandra problem, but what are the implications of that for like the future development of AI systems? And I think particularly in terms of like trust and decision making.
Yeah. I think it's a huge difference. Fundamentally, I think I said at the beginning of our conversation that context-aware model weighting has existed in centralized settings. But in centralized settings, it is less important because you don't have your data and model privacy. In decentralized settings, this is a really fundamental problem. And by solving it, basically what we've done is we've given the potential of decentralized AI a complete coordination upgrade. It's not a model upgrade, it's a coordination upgrade. It basically introduces the ability for swarms of models to together become, to be selected better. So that changes completely how you can scale model swarms. Previously, there was no point in scaling model swarms because if you just take the average, then scaling the swarm is not going to get you anything. But now, because you've learned to listen to the right model, you actually benefit from growing that swarm, because the further you grow the swarm, the more likely it is that you have an expert within that swarm for the rare event that you're facing right now. And that scaling challenge is unlocking an enormous amount of potential, because we're using AI systems in the world for all kinds of things related to simple forecasting to tail risk events. And especially the tail risk events are where AI, of course, shines. Like AI is capable of detecting patterns that are hard to detect otherwise. And it's precisely there where you want the experts, where you need the experts, and where you can only succeed by actually harnessing the power of that swarm. So that is why solving the Cassandra problem has been such an instrumental step forward. It makes this sort of long tail competence where you're capable of predicting this tail risk, it makes it economically sustainable. Cassandra, even though she had a rich dad, no longer runs the risk of going bankrupt by just going on about that horse. It basically, you can now have a whole swarm of Cassandras that are each economically sustained. So the consequence of that is we have this swarm that scales. So the swarm becomes an expert in everything. And that also means that now, in terms of trust and AI systems, we no longer have to worry about distribution shifts. We no longer have to worry about system shocks. No, all of these features in real world data become measurable and actionable. Like you can respond to them. And there is no single best model. There's only a best model for the circumstances you're in right now. And that diversity of thought, don't care about diversity of identity, is totally irrelevant. I don't care if your model is called Jim or whatever else. I care about the fact that it thinks differently than all the other models, is an expert in something that all the other models are not an expert in. And that form of diversity becomes the power of the swarm. And that's what swarms were always intended for. It just, we didn't really have a way of coordinating these all over the world. And by combining this form of context-aware performance forecasting with the incentive structures that support and reward these Cassandras, we've basically unlocked a future where all of these different talents and skills and specializations coming together result in more resilient and more capable, and in the end, much more trustworthy systems than what we had before.
Yeah, I mean, that's super exciting. You painted it's quite a revolutionary picture, and yeah, it's really exciting. But I guess my last question is taking that, building on that. We've got this picture. So, but what is it does solving this Cassandra problem unlock for the AI systems? Because we're starting to make higher stakes decisions in messy, like shifting real world conditions. So you've described that in I guess a sort of conceptual way. But how does it help in these high stakes, messy real world conditions?
Yeah, I think this is a really important question because it alludes to something where I think we just need to think differently about AI relative than to what seems to be the norm these days.
Yeah.
Like we often talk about AI progress in the sense of like bigger models and better benchmarks. And the Cassandra problem is pointing really at something more structural than that. It points at a failure mode of AI in general, where the system learns to trust what is popular, what is stable, what is the average, and basically at the same time it's just discounting the specialist that is right now when it matters. And that results in this sort of it makes AI this expensive consensus mechanism. That's what I always like to call it, because it's all it is. It's a popularity contest. So that matters because the real world isn't stationary. The real world has this tendency to shift exactly when it matters, right? The moments that really define the outcomes, define the future, are regime shifts, are rare events. They are the unusual edge cases. And they're exactly the moments where you want your system to be able to say, hey, stop. I know who's right in this situation. And when you solve Cassandra, you're addressing that directly. And you're not just improving the accuracy, but you're improving judgment under uncertainty. And that is, from an end user perspective, is the fundamental step. Now, what I think is the most interesting about this is it changes the way in which you can build trust. And I was talking about the scalability of the system earlier, right? The fact that now it makes sense to scale and grow the swarm of models because you invoke all of that domain expertise at the right moment. So because of that, trust stops being the same as saying like, oh, do I like the average response I'm getting? No, it becomes, does this system that I now have, does this swarm reliably surface the right expertise? Does it expose the right expertise at the right time and at the same time reward it so that it keeps showing up?
Yeah.
And if we get that right, we can move from the giant monoliths that the frontier AI labs have built, this monolithic form of intelligence, towards a world where many specialized models can coexist, compete, and coordinate, and strengthen each other without being silenced by the majority. And I think we're going to see a huge amount of acceleration in that direction over the next couple of years, and in particular because monolithic AI models have hit a ceiling. There exists a fundamental ceiling that you cannot break through without harnessing the capabilities of the context-aware swarm. No monolithic model is going to solve that problem, but the swarm will, and that's where we're going.
Amazing. All hail the swarm. Well, that's quite a picture to finish on. So I think this is a great place to bring us to the end of this episode on the fascinating Cassandra problem in AI and Allora's role in solving that. So thanks so much, Diederik. I massively enjoyed that. I think going back, so we're discussing how the consensus aggregation suppresses rare but high-value expertise, and I guess Allora's forecasting and performance forecasting, the context awareness of the inference synthesis, and that combination of those that surfaces as the Cassandra signals, the one that you're mentioning about in terms of the swarm context. We covered, I think, particularly important, the incentives, how they matter, and if you want to keep your Cassandras and the expertise they bring to remain active in the system. And I think it's really exciting how Allora's going to lead this this development of the swarms and the overcoming the fundamental limitations of these monolithic current systems. So thanks again, Diederik. And if you'd like to go deeper, as we mentioned before, there are, you're going to read the research papers, all the additional literature on this, and this will all be available on at allora.network/research. So stay tuned for the next episode of the Allora Research Fireside Chats. Until next time.